Hello, welcome to Electronics Education. This is Vincent Chang. In the previous two lecture video, I teach you about the first two topology, the Series-Shunt and the Shunt-Series. And this one, feedback profile, Series-Series, last two topology and Shunt-Shunt should be quite easy for you. Because we can just simply take the conclusion, the lesson we learned from the past, and just apply and organize. And skipping, and without doing any mathematical derivation. So this lecture, I promise you, is going to be very easy. So ideal, let's quickly review all the feedback topology. The first one, the ideal series, mixing, shunt sampling. So what amplifier associated with this? It's the voltage amplifier. The second one, the shunt series feedback. So it's the current mixing and then current sampling. So current amplifier. The third one, the series feedback. So it's the voltage input and current output. Conductance amplifier. The last one, shunt mixing, shunt sampling. So it's the current input and voltage output. So shunt feedback as a resistance amplifier. For the ideal series shunt feedback, the whole structure on the left-hand side, so we can sort of consolidate and try to simplify the whole circuit, the whole feedback, series shunt feedback, into a simple version on your right. And three parameter pop up. The first one, the closed loop input resistance is going to increase. And then for the gain relationship, it's going to unchanged, remain the same. And for the output resistance, because the nature of the shunt sampling, so cause the output resistance is going to go down. It's going to go down. This just reminds me, let me ask you another question. How can you do to make a better voltage amplifier? So teacher, what do you mean by that? A good voltage amplifier should have what input resistance or what output resistance? Tell me this. For a good voltage amplifier, this is the concept. For a good voltage amplifier should be the higher, the better, right? Right? And also, what about the output resistance? Should be the lower, the better. So, if you are not satisfied with the voltage amplifier in front of you, you think about the input resistance is not high enough, the output resistance is not gonna low enough, then what can you do? You can apply feedback. Apply what feedback? Series shunt feedback. Because the series mixing will increase the input resistance. And the shunt sampling will reduce the output resistance. But what should you compromise? The gain. The gain will be reduced by the same factor of 1. So it's all about trade-off, all right? But I think you got the concept. Same thing with the shunt series feedback. The shunt series feedback, you can consolidate 3 components. So the shunt mixing cause the input resistance goes down. The relationship for the gain, unchanged. But the output resistance is going to go up. So the same argument can apply to the current amplifier. If you are satisfied with the input resistance and the output resistance of your existing current amplifier, maybe you can consider applying the feedback. What feedback? The shunt series feedback, because it instantly make the input resistance go down and the output resistance goes up. So now this lecture is about the series, the last two topology, and the shunt. For the series feedback is the series mixing and series sampling. Voltage in and current out. So voltage input Vs and then current out Norton on the right. Norton. But the AG on the G, there's a subscript G. The G means conductance. So AG means the transconductance. So the AG on the left is the open loop transconductance. The AG on the right is the closed loop transconductance. So for the closed loop transconductance. So now, because you can just apply the lesson you learn. Because you are experienced right now, okay? You have gone through the previous two topology. So you can just apply the lesson. You learn from the past. For the series mixing, it's the series, so go up, right? Times the 1 plus A beta. But what is the A here? It's different from the previous two topology, right? Because the meaning has changed. From voltage gain and current gain to now it's a transconductance. Also the beta, what's the dimension for beta here? It's the resistance. So when A is the transconductance, beta becomes a trans resistance. Check the circuit diagram on the left. See, the current sampling is the current sampling. The series sampling is the current sampling going through the beta, and then times a resistance generate a feedback voltage, VF, right? So beta, in other words, the product of A times beta always dimensionless. Always has no dimension, all right? So only the dimensionless can add with what? The dimension is 1, the number, the 1. This is unchanged, but the A has a meaning of conductance. For the output, what about the output resistance? For the series sampling, it's going to go up. It's going to go up. So RO equals RO times 1 plus A beta, ideal series. For the ideal shunt feedback, so current input, current mixing, and voltage sampling. So it's the trans resistance amplifier. So again, so now it's the shunt mixing. IS minus IF equals II. Times AZ, trans resistance becomes VO. So sample VO times beta G. So when A is the resistance now, beta should be a conductance, right? And then again, it's the equivalent circuit over the what? Of the shunt feedback amplifier. So 3 parameters pop up. Number 1 is the closed loop input resistance should be reduced because it's the shunt mixing, and then unchanged for the trans resistance relationship, and then for the output resistance should go down as well. Ideal shunt feedback. So pretty easy, right? So for takeaway for the feedback topology, we have the 4 topology. 2 types of mixing and 2 types of sampling. So it's time for you to wrap up the 4 topology for all things together. And then ideal series shunt is the voltage amplifier going up for the input resistance, going down for the output resistance. Voltage gain in the middle, unchanged. For ideal shunt series feedback, it's the Norton current amplifier. So pay attention to the short circuit between G and H All right, there's no external load. For the RF, shunt mixing go down, unchanged, and then go up. For ideal series and Shunt-Shunt, the one that the two topology we focus on this lecture video tells us transconductance amplifier, and then RIF, transconductance, and then RF. The final one, the shunt feedback, trans resistance. When A is the amplifier is the trans resistance, the dimension of the beta should be conductance. So the RF should go down, and the RF will go down as well. So it's quite easy for us to put all things together at this moment. But moving forward, it's going to be more challenge. Because the question here is, so far, I teach you 4 lecture video around the feedback, but it's all about ideal case. But what about the practical situation? This is, moving forward, we're going to focus on how to solve a practical feedback amplifier. So I'm looking forward to seeing you in the lecture in the future, in the lecture video in the future. Thanks for watching.